particular problem from additive combinatorics, we would like to find a precise solution of it. So I will share this ideas of us. So we have a subset of a group, or you can think about it like a finite subset of integers, and we consider intersections of the following form: a minus s, and we want to find the maximum of such intersections. Of course, the maximum is if I take s equals 0, then the intersection is a. So I want to study this quantity, this maximum. A can be also a body, for example, and here I need to talk about convolution of my characteristic function, and s or minus s is not important. A few words about the motivation. The motivation comes from a rather well-known theorem of Feynman. In Fixtus, who studied the following problem. Consider central object of additive combinatorics is the set of all possible sums, and we want to understand the structure of these sets in the case when cardinality of A plus A is small comparable to size of A. So, for example, if A belongs to G, then A plus A is at most to A minus 1. But can I replace, and the equality holds if and only if A is an arithmetic progression. But can I replace this constant 2 by something larger and still say that A looks like an arithmetic progression or a large subset of an arithmetic progression? So the famous theorem of Feynman says, it's so-called 3k minus 4 theorem of Feynman. Say that if I have a subset of Z, A plus A at most 3a minus 4, that's because 3k minus 4 here, then there is an arithmetic progression such that A is a subset of my arithmetic progression P, and P has size A plus A minus A plus 1. Everything is optimal. This theorem 3, 4, and size of an arithmetic progression of less P. This theorem is just the first result in a series of theorems about structure of sets with small doublings, so with small subset. This K now can be not just 3 but tends to infinity with some speed. So it's a classical subfield of additive combinatorics, and this question about maximum comes from another classical subfield of additive combinatorics, namely solutions of linear equations in finding monochromatic solutions of linear equations. Isaiah Schur, his attempts to prove Fermat's theorem, he considered the following problem. Suppose that I have a coloring of Z, a finite coloring of Z, that is a disjoint union of Z onto K colors. Is it possible to find a solution of this equation such that X, Y, and Z belong to the same color as G? In other words, can I find a monochromatic solution of the simplest equation? Yes. So okay. So the simplest method how can we calculate the maximum is just average. So suppose that I have suppose that I consider just the sum over all possible s. So this sum is non-empty if and only if I can solve this equation, and it means that s can be represented in the following form. In other words, it belongs to the following difference set. So the summation here is taken over a minus a, and it's easy to see that here I just count the number of pairs a and a prime, the number of all possible pairs. So in our finite case is a squared, and it means that there is s and 0 such that this intersection is greater than a minus 1. And if I write k for this expression, I see that this is more or less a over k. Okay. So you can think about this problem not in Z, but in general group. So if A is a subset of finite abelian group, say, then by the same method, I obtain that there is non-zero S such that this intersection is greater than a squared over size of G. So so you see there is a difference between these two problems. I can think about say take the simplest group Z over N Z, say, and here I obtain a squared over n. But if I indeed live in Z, namely in this initial segment from 1 to n, then I need to divide this quantity by 2n, basically. So there is the difference, and it's obvious why we have the difference, because of each effects. In our group, we have no any edges. It's all elements are equal somehow. So I want to show you that actually in this problem, there is no difference between group and our initial interval. So you can basically improve this bound by 2. And of course, this is optimal because there are plenty of counterexamples. You can take a random subset of this initial interval and so on and so forth. So to me, it's an interesting problem because we somehow finding something which cannot be obtained taking just expectation. Okay, so let me formulate our result. So say suppose that we have a subset of initial interval, suppose that a minus a equals just less than 1 plus delta, then there is S non-zero such that and very small and this quantity, and this quantity actually can be calculated. It's something like 2 delta. The same is true in FP. Here we need to have the following condition. And K then the same. Also, our method is so as I said before, the set of these shifts is has a zero measure, and actually you can construct some examples like that sure that exactly the set of this S is less than a minus a, is smaller than a minus a. And the same can be proven for functions and for higher, for larger number of shifts. Under the same condition, F so they're different and non-zero. Such that greater than 2 to the k minus 1, k minus 1. Okay, so about the proof. The proof comes from the higher energies method. So let's look onto our set of difference as the set of all S such that a minus a such that this intersection is empty, and then this set can be generalized as follows. Consider the following set, the following multidimensional set of shifts. So if you like dynamical systems with the set of recurrence times and with the set of multiple recurrence times. So it's so-called high dimensional difference set, and it can be rewritten in terms of normal difference. Namely, it's easy to show that this is so the subset of, if we are in our group, it's a subset of it's a subset of Cartesian product of my group. So you can rewrite this set in terms of ordinary differences. So a k minus 1, it's the Cartesian product. And this set is so-called diagonal set. It's a very tiny set, one-dimensional set. For the form A is taken k minus 1 time. And you see that this difference is very asymmetric, and using the effect you can play on this and obtain. So I'm trying to say that these high dimensional sets, they're very different from one-dimensional ones, and you can use some special structure which is inserted in such sets. So, for example, consider the following set. It is all integers from 1 to n. So what is a, say, squared minus delta a? So that is a, yes, and after that you need to shift my set by this diagonal set, and we obtain this hexagon. So you see, of course, this set is a subset of minus n squared, but it's a proper subset because you do not need in these two parts. And in higher dimensions, if you consider, say, a k minus delta ka, then you need to write something like a cube and you need to shift this cube. And again, my multidimensional difference set lives in my cube minus n to the k, but of course it's a proper subset because you do not need to include this part of the cube. And of course, the volume of this set tends to 0. I mean, if I divide it by the volume of my cube. So that is actually the idea of the proof, that in my calculations I don't need to consider this red part of the cube. So that's the proof. So as in our initial step, consider the averaging over our high dimensional difference set. Of course, size of this set is a to the k. Yes, but I can use Cauchy-Schwarz and try this as the square of this intersection, you can think about this intersection as the high dimensional convolution of the quadratic function of A. So it's something like C1 as K minus 1 times the support of my high dimensional convolution. Okay, so first of all, I want to return to the intersection of A and its shift, and here we have high intersection. So there is a lemma. It's called duality. That the squares of such convolutions, and moreover, all powers of my convolutions, they enjoy the following property. So you can switch these indexes as K and L, and it means that basically this guy is just A plus S minus S to the power A, because this index 2, this square 2, says me that I need just one, I need to consider just one intersection. So that is basically more or less this maximum, or at most maximum, of our intersection to the K. Actually, this one, but the main task is how to calculate this quantity. And here we have this gain. We can estimate this size of our high dimensional statement trivially, and our proposition here is the following. So it works in FP as well. Suppose that we have a set. So let me just formulate the corollary of our proposition. So if at most where A bar is a set of the same cardinality and A bar is an interval centered at the origin. Okay, so this so it holds for any A in Z, but as well in FP if I say that P is greater than 5 and my A is less than 2 or 3 times P plus 1. After that, you calculate this quantity for the interval, and you substitute this . So let me denote this maximum as M. You substitute this maximum, this inequality for maximum into your initial estimate. So here I have Ka to the E minus 1, right? But this bound is just the volume of this cube, and removing this red part, I can divide it by E minus 2 and multiply it by 3 of K. So taking K is a parameter. So taking sufficient large K, you obtain this result. Also, I should say a few words about this corollary. It's completely not trivial. It comes from Hardy-Littlewood theorem. So they proved that if I consider any linear equation, AJ belongs to AJ, then the maximum of the solution to this equation, then the number of this of solution of this equation doesn't exceed the same number where AJ equals AJ bar, where again AJ bar are intervals centered at the origin of the same cardinality. It holds in Z, but it can be reproved realized to FP. It's not obvious, but nevertheless, and that's why we need some restrictions on size of A. But nevertheless, you can show that the worst case is when my set A is an interval, and after they substitute everything and obtain the result. So it's funny that this constant 2 is optimal, and the slogan here that it's never it's taken an expectation, but in the sense of higher energies, not in the sense of naive, simple one-dimensional expectation. That's all.
Any questions? I have questions. So for your theorem 1, what about the converse? Like how small the delta has to be?
Like small what?
I mean, let's say if you have a set A and the sign of the difference of set is less than A times log A, that's probably not true anymore. Am I right?
Any random set gives this bound. So to say something in inverse direction, I need to have deal with all random sets.
No, I'm thinking about, I mean, like, not random set, I mean, a set A where the different set is very small, like less than A times log A. Is it true?
No.
No,
It's just this condition with delta is just technical one. There's no any deep sense.
Other questions?
What happens if you replace